I think actually this is my first time actually using this recording feature. So I guess it should be recording. It's being recorded. So let's see if it's not, then I'll see if I can find another version from the previous offering of this lecture. Hopefully it is recorded. Okay, so we have seen two kinds of graph models. One is called edge label graph, and then this is called the poverty graph. Um, so here, really exactly same thing. Just quickly recap. We have a label for each node and edge. Label here, for instance, we have label a person, and edge we have x in for edge. And then we have a set of key value pairs, which called attributes. Like in this case, for instance, this E1, we have two attributes. One is row and Michael G. Scott, and then there's a reference, Wikipedia. So the difference between these two models is really is the following. The first one is that having node labels as part of the model can offer a more direct abstraction that is easier for users to query and understand. So Steve Carl and BJ Novak can be labeled as person. So so for instance, if it really don't really have any context at all, then we may not have any ideas about like what's this node trying to represent. Like, I mean, in this case, it's obvious that, okay, this is actually a person name. So this node represents some person. And then, for instance, like the office, it may not, it may be represents, some office, or it may be represent, like in this case, a TV show. So that's can cause a little bit of confusion. The second is that poverty graph actually is suitable for scenarios where various new type of meta information may regularly need to be added to edges or nodes. So in this case, so if we want to add a third attributes to this node, we just append another key value pair at the end of this. And compared to the previous model, there's really not a straightforward way to do that. So let's just briefly talk about the difference between graph and the relational model. Okay, so why do we need a graph if given we already have, like, say, a relational model? So one nice thing about a graph model is that it can be really easy to combine information. Like, say, for instance, we have one graph. Here we have a TV show, and then we have a year. And then they will have another part of a graph, say, this is BBC, and their executive producer, Ricky Gravis. And then we want to say there's some connection between these two parts of graph. Then basically what we can do is very simple. We just, like, say we add one more edge, say produced by, then we can combine two graphs into one. But however, in analogy here, in SQL or in the relational model, to make such connections, we can just add, say in this case, we add foreign keys, like one reference to the other. So one is, this part is modeled as a table, then we add a foreign key, and then model this part as a table as well, and then the foreign key make the connection. So to give a more straightforward view, so we have this another set of tables. You implement the exactly same graph. It's exactly the same graph, and then we're just adding foreign keys to make the connection. So in summary, the graph structure actually is more intuitive than a collection of tables. Like you probably have seen how we can use relational table to implement org chart, but that may not be very straightforward to see. That actually is the organization chart. And second is that there's ambiguity in graph representation using relation model. Like, for instance, given a table, whether its models are directed, all the entries in it actually is directed edges or undirected edges, can be confusing. The third is that we can actually avoid repetitive data storage from user perspective. So say we don't really need our foreign key or primary key in graph. I'm not saying that we don't need, I'm saying that we don't really like make it like explicit, like say after you create table, you just need to explicitly specify, okay, this is primary key and this is foreign key, and we make such connection because the graph is such connection is already built in as part of the graph model. And also, in the relational, like if you under the same, say same schema, like a database schema, like basically you cannot have two tables with exactly same name but with different kinds of attributes. Say we cannot run the following two cycles one by one. So first one is called TV show, then we have a title year as attributes. Then we want to create another TV show that has a title year and production company. That is not really possible. And lastly, property graph may offer some nice query languages for graph problems that we'll see later on. So one more point is that data modeling is still really relevant in graphs. So suppose we have this following graph, but you still need to have some like like modelings specify the multiplicity, for instance, between like two nodes. So basically, the takeaway is that whatever you learn in the class, in the relational model, that gets directly translated into the graph model. So let's talk about this, our kind of like concrete implementations of a graph database, which is called Neo4j. So Neo4j is a graph database that uses property graph data model with a query language called Cypher. So in graph database domain, there's really no standard query language yet. Actually, that's a lie because they just make a standard. I'll talk a little bit briefly after this slides, I think. So there exists like because the recently published standard, but there's still like a current landscape is that like there are many kinds of flavors about the query languages. Say for example, like for RDF, the RG so the edge labeled graph, we have a query language called Sparkle. And for the property graph, we actually have two or more, possibly more. One is called Cypher and the one is called Grammarly. So suppose we want to say, given the previous model, we want to find the previous graph like this three nodes, three edge graph we saw earlier. We want to find co-stars of the office. So for the Sparkle, we probably write something like this. I don't really go into that detail. And then we have a Cypher, which writes something like this, and then we have Grammarly. As you can see, those are very different flavors, like to express the same query. So today we're going to focus on this green one, which is in some way similar than the rest. So just a little bit talking about this standardization. So there's an ongoing standardization effort, just like SQL for relational model. We want to create some like unified language for graph model. So there are really two efforts. One is called graph query language, short for like GQL, which is completely new language for graph database. And there's another effort called SQL PGQ, which PGQ stands for property graph queries, which extend SQL with the graph query capabilities, like for instance, path finding, pattern matching. Those two are as a whole is part of standard, meaning that in the future for any like graph database, you can either write GQL, basically completely new language specific for graph, or you can just use your write your familiar friend like SQL, but enhanced with graph query properties. So the following is really a timeline. So this right now is I forgot to update this cross. So actually we are already in the Q3 of this year. So that means that SQL PGQ released just last quarter. And then the next quarter, early next quarter, like Q1 next year, we're gonna see GQL release. So those language will have majority of the feature will really the same as a Cypher with a slightly more different syntax. So it shouldn't be that hard to pick up those two new languages after today's lecture. Okay, so let's just create our first property graph with Neo4j. So let's just walk through this this quick demo. So suppose we have our graph. We want to how we can create this graph in Neo4j. So the syntax here is just we want to say sorry about that. So we have a create, and then we have just write out the bunch of nodes. So here we have a nodes n1 person is very straightforward translation of this graph. So we have n1 person, the parentheses means that this is a node. So we have n1 person, it has a set of attributes. Like say in this case, we have name and gender. And then we have another node n2, which is person, and we have another attribute called BJ Novak and male. And then we have again the third node TV show, and this has title to office. Then after we create all the nodes, we just make the connections, meaning that adding edges to those to make to the graph. So here, for instance, we have n1, which n1 here again parentheses means this is a node, so n1, and then this is actually direct edges n2, and then we have this x in like this is a label. So label here is an x in, and it has two key value pairs. One is called row Michael G. Scott, and there's a reference Wikipedia. Similarly for the next two edges. So notice that in the Neo4j, there's only exists like when you create a graph, there's only like the directed edges. So basically every edge has a direction. But when you're doing query, you can optional like say ignore the directions, only focus on indirect aspect of the edges. Okay, so let's just do a little bit practice. Okay, so let's let's create the organization chart of the paper company Dunder Mifflin Scranton branch in the office. So all edges have I'll show the organization chart immediately. So here all the edges you can have labels EI managers. Just so basically every edges will have label managers. And here are some useful commands. Say you want to see the graph, you can run the following commands. If you want to delete the graph, you can run this following commands. There is a chance that you probably need to create a list, meaning that the key value pair where key is some string and value is actually a list instead of a specific string value. So here, for instance, you can use angle brackets to create those lists. For instance, if you have a key like say row as your key, and then the value can be like sales or assistant regional manager. Okay, so let's spend maybe like 5 minutes just to like to create this graph. Just play around with the sandbox. Okay, so here is the organization chart for today. So afterwards I'll just post a series of commands you can play with. And meanwhile, let me upload the slides as well. Yeah, feel free to let me know if you have any questions. So just by the way, so if you like say want to already upload the lecture, so if you actually want to see there's already have some comments, so you can just click on this lecture notes from last year, and then you can click on this graph DB queries. Then there's a bunch of queries that you can run. Like for instance, in this example, I think like this one, uh actually I think this one will be the comments that actually create this graph. So if you already want to see the answer first, then you can just take a look at this file and run those comments in the sandbox. Okay. How's everyone? So how does everyone like get the chance to like at least create part of the graph? So like let's you can just take a look at those folders. Like there's a that specific file to just play around with it. I think there's a chat actually from the previous Zoom session that professor leaves some message that he wants you guys to take some screenshots. So I guess it's probably the perfect chance to take a screenshot of your sandbox running command, like running screen, even though like there may be some errors. I think that's fine, I guess. So let's talk about graph query languages. So there are two important usage patterns for graph query languages. One is called graph pattern matching, and the other is called graph navigation. We'll focus on Cypher in this tutorial. However, any significant graph query languages will have these two important patterns in their languages, albeit that they may have a little bit different syntax. Okay, so the first one is called graph pattern matching. And the graph pattern matching, so a match is actually a mapping from variables to constants such that when the mapping is applied to the given pattern, the result is roughly speaking contained within the original graph. So for instance, let's say again our query is to find co-stars of the office, and here is the graph we already have, and actually this is the graph patterns like implement the query find co-stars office. So it's almost identical to the graph. So here we have the TV show and it has titled office, and here we have again the edges axing, and we have a nodes person, x1 person and x2 person. So here x1 and x2 actually are the variables we just don't know. So we want to see what kind of part of the graph has the following pattern. So basically we want to map, as you can see here, we want to map x1 to here to this node with name Steve Carl, and then we want to map x2 to this node, BJ Novak. So the other way around also works. So meaning that if you actually flip this, because this is kind of like a mirror case here. So if you actually flip, flip this graph patterns, then we can have x2 match to Steve Carl and then x1 match to BJ Novak. So this is actually exactly the answer to the query. And then the result set, normally we talk about, okay, the result set for SQL, meaning that the answers after running a SQL query. Here we're talking about, we call this as a matching. So matching for Q1 is exactly the same as result set for Q1. Okay, so here the Cypher has this no repeated edges back semantics, just for your awareness. So let's just take a look at this query in details, how we can implement this pattern in Cypher. So here we have this, again, we have this query. So this query actually is a Cypher language that actually implement this query, implement this pattern, which means that implement this query. So if you want to, in other words, if you want to query the graph using for the following query, find co-stars of the office, then basically you just type this thing in your sandbox. Okay, the first one is called match, meaning that, okay, they will specify we want to do a pattern matching query here. And then here we have x1. X1 is just some variable name. We have a x1 person, and then we use a parentheses, means that this has to be some node. And then we have this x in, and then we have this angle brackets, and we have these edges. Then we have another node, which is TV show, and we have title the office. And this means that, again, the parentheses means that this is some node. And this node is fixed because this node has a label, and it has to, basically here, there's no variables inside this node. That means that it has to match to a specific node in the graph. And then we have another axiom, and then we have a person. As you can see here, it's a very kind of like, it's like ASCII art, meaning that you just directly describe this graph in words. So here, the direction here actually matters. Here we have a node, and it has to have goes from left to right. This edge has to go from left to right to this node, like a TV show. And then we have another edge, which x2 node has to go, edge has to go from x2, meaning that from right to left, x2 to the TV show. And then the way I want to have return, x1, x2. Okay, so here match, and then we want to match variables x1 to nodes with no label person, and x1 has to connect to TV show nodes through an incoming edge with edge label xc. So there are the syntax. This is a major feature of the Cypher syntax, but there you can feel free to check out online on their Cypher menu. Okay, so maybe let's just spend like 3 minutes to think about, or even just play around, like how we can implement these two queries in Cypher. The first query is called who's inside party planning committee PPC. So here PPC is a department. And the second query is how many people does Michael directly manage? There's a special built-in function called count, exactly as a counting SQL, which counting the number of returns. There's a chat. But how do I find it? How do I find the Neo4j statements? Yeah. So here, so here, actually, it's not this one. So here is under this box folder. There's a there's a directory called lecture for notes from fall 22, and there's a subdirectory called GraphDB queries, and there's a bunch of them. And this one is for the organization chart from the previous slides, and you can run this to create the graph in your sandbox. Okay, so let's take a look at those queries. Make sure at some point you take a screenshot, like in case you missed the previous chance, you probably need to take out probably one is sufficient. So the first one is called who's inside party planning committee. So here we have the following Cypher query, which basically very simple. We want to match all the nodes. So nodes is p person, and where we can have a where syntax in the Cypher as well, where party planning committee in p.dept. So p.dept, so dept is actually a key. And here we want to say the corresponding value has to be party planning committee. And then we want to return p.name, meaning that we want to basically p here is the variable and say it's a kind of like pointer to this specific node. So we want to return its name. And second query is that how many people does Michael directly manage? So here we have to write some graph here. Okay, so we have some graph pattern here. So we want to match p person, which is node, and then we have a label manages, and then we have another node which n, and n is also person. So here and also this direction has to be n person goes to p person, and then where n.name is Michael Scott, and we return count p, meaning that how many person that actually is how many people actually is managed by Michael. So let's just do one more. Let's do one more practice. There are following two queries. Find all the employees that are directly managed by someone that reports to Michael. And the second is does Michael directly manage more employees than Jim Halpert? Let's again spend 2 or 3 minutes. Okay, so let's take a look at those two queries. The first one is find all the employees that are directly managed by someone that reports to Michael. So it's a little bit slightly complicated than the previous one. So here we have our pattern is P, which is name, Michael Scott, and then we have edges, which with the label managers. And here we have some new thing here going on here. We can actually using this empty parentheses to indicate that, meaning that any node works, meaning that we don't really have any preference on what that node is as long as there's some node in the graph. And then such node has to be managed by Q. And then we return Q.name. So here you can just basically, write this pattern and then match directly as the query. And second is second query is does Michael directly manage more employees than Jim Halbert? So here we can have, actually, let's just ignore this for now. So here we can have multiple match. I can call it I call it match block. So we have a match where with, and then we have another match where, and then we return. So here let's take a look at the first one, first block. So here first block is a P person, and then we have N person. So N person manages P person, and N.name is Michael Scott. And then we use another keyword called with count P as C1, meaning that we count how many P, basically how many nodes are there, and then we count the number as C1. And then we write another match block which has a similar pattern, which P person manages M person manages P person, and then M.name is Jim Halbert, and then we just return whether C1 is greater than count P. So each match where can be thought as a select from where in SQL. Okay, so here there's a slightly language feature here that we have this with, which it kind of like you can think about it mentally as a kind of like a breaker, meaning that it's a break. Basically make a break between these two. Basically, as you can see here, the first match here we use this P, and then we use a P again. But with this with, that means that this two P can be the same. It can be the difference. It doesn't necessarily mean the same node. So you can just to play around with this query and see what's you're gonna have after you remove this with. And the second language pattern, as we saw, the first one we just saw is called graph pattern matching, and the second is called graph navigation. So it's a mechanism provided by graph query languages to navigate the topology of the data. So there are two important query classes. One is called path query, and the other called path query plus graph pattern matching, mean that you kind of combine these two features together as one, using these two features at the same time within one query. Sometimes this is called navigational graph pattern. So previously we match a graph pattern. Now we want to match a path pattern. Essentially, there's not really much difference, as you will see. So the path query here has this generic form. X goes to Y, and there we have some alpha above the arrow. And alpha is some specified conditions on the path we wish to retrieve, and X, Y are the endpoints of the path. So normally these conditions are expressed using regular expressions. So let's take a look at the example. So here we have this again. We have this our running example of office crew graph, and then we have our query find co-stars of the office. And then basically that means finding co-stars of the office. Here we're basically saying that whether there's another person, one person that's goes to another person has this conditions called xing to the minus. So xing here is that basically dot here in the regular expression here means concatenation, meaning that we put two labels together side by side. And this minus means that is kind of like direction. So by default, edge goes from left to right. So that is this axing is meaning that this axing represents some edge. It goes to left or to from left to right by default. And if we want to specify the edge goes from right to left, then we basically put a minus sign as a superscript to a label. Okay, so let's take a look. So here, Cypher has no repeated edge back semantics. So we want to find this again, this query, and then we have this almost exactly the same as the previous graph pattern matching query. The only difference is that we put a pass or some like name, and the equal sign before the pattern here, which indicate that okay, we want to find the pass instead of finding the specific nodes. So the return here is by pass, meaning that as you can see here is that I actually will list basically list out the paths by definition, like the nodes and edges. So the start point, for instance, take a look at this. The first row here, the start point is Steve Carl, and then it has to go through this this axing edge, and then goes to another node, and then goes through the axing edge again, and then go to the this node BJ Novak. So it's really nothing new, but instead we just return a path instead of a set of nodes. So we can combine path query with graph pattern matching by allowing edge labels in the graph patterns to be path. So again, so for instance, we have this Q2, we want to find all the people that Michael Scott manages. So this pattern will look something like the following. Here we have this node where you have n1 person, and then we have another node x1 person. X1 is some node we don't know, so that aspect is graph pattern matching. However, we want to return the path, meaning that we want to return the all passable path that goes from n1 to some node, and it has label managers. So to write such queries, we can write some query like this. So we have this p person. P person is something the fixed. So we have p person, and then p dot name is Michael Scott. So that node is fixed, and we want to have it goes through multiple hops and goes to another node, which q person q is some variables we don't know. And to specify multiple hops, we have this. We can just write managers, which is label, and then we have star, meaning that the previous label managers can appear one or more times. So one or more times is like one dot dot. So if you have in the later on, we'll see how we can specify 0 or more times. So let's practice. So the first query we want to take a look at is called it's a query. It's called like get the Dunder Mifflin employees that are on the same level as Michael Scott. Okay, so here's a one built-in function called length that will basically returns you the length of the path. Maybe we can spend 2 minutes to just think about or you can write in your sandbox to see, play around and how to write this query. Okay, so let's take a look at this this query. So suppose we have this match. So we have two match block here. One is called P1, which n person matches which P person matches n person. So and then we have P2, and then we have P person matches n person, and then we have our where class where have where length of P1 equal to length of P2, and n.name not equal to n.name, and n.name equal to Michael Scott. Then we return it. Okay, so essentially, we can actually exact query the same data in relational model. You can just feel free to take a look at this called SQL dot exercise dot dash exercise dash 2.sql in the same folder. So let's take a look at another query. So get the Dunder Mifflin employees that on the same level as Michael Scott. Okay, so exactly the same, exactly the same query, but actually we want to implement on the relational model. So here, actually, we want to this is actually you can see this is much more complicated than the corresponding Cypher query. Instead, actually, this is called recursion in SQL. So we want to have some base case here that if two people are at the same level, their manager has to be the same, and then we specify a recursion, meaning that same idea as base case, but use the base relation and the result table we just computed in base case to form this recursion, and then we return necessary values. So the point is that actually this recursion query looks much more complicated than the corresponding Cypher query. Okay, so let's just take a look at the two queries. So in this case, the first one is does Jim Halbert match Phyllis Slavin, and then the second one is find all people that indirectly matched by Michael Scott. So the first one is that okay, we want to find again the path that P person has to goes to like some Q person, and P down name is Jim Halbert and Q down name is Phyllis Slavin, and then we return basically count if any such path exists. And for the second query here, we want to say P1 person, and this is Michael Scott, and then goes to some goes to one or more hops, goes to some node, and some nodes goes to one or more hops to P2 person, and then we return the distinct P2. So just use keep thinking about why do we use distinct P2 rather than distinct path. So actually, you can. There's one more. We already talked about two features. One is graph pattern matching, and then there's a navigational graph. And then actually one significant kind of feature of Cypher is that you can, or any graph query language, is that you can directly use graph algorithm inside the query. Say, and Cypher and many query languages allow user to directly embed graph algorithm inside the query. So for instance, we want to find the shortest path between David Wallace and Andy Bernard. And this is actually the following the query. So here, basically here we want to say there are two things going on here. We want to say there's a path between David Wallace and Andy Bernard, and also we are interested in the shortest path. So here, this pattern here, P person name David Wallace goes to Q person Andy Bernard. This is actually the pattern, and we are interested in the shortest path, meaning that this is actually a built-in function, which is a graph algorithm. So you can use more graph algorithms like PageRank, centrality, connect component algorithm, etc. Basically in the same fashion as this, you just call the algorithm itself, and then you put some patterns as an argument to the algorithm. So the next we're gonna talk about how we can understand the Cypher query, meaning that like how we can be troubleshooting, like say if there's any performance issue, how we can troubleshooting. So Neo4j has the explain command, so just like explain any like RDBMS. So the following basically running example like for this section. So we have basically we also have 3 nodes R3, R2, R1, and we these are a bunch of values. And then we basically run a natural join query, join these 3 tables together. Of course, it is actually specified in the relational model. So we can have some plans. In this case, we just run explain command to see what's the output, what's the plan of the query is, and we can actually directly map the relational model to the graph model. So just some guideline is that a row is a node and a table name is a label name. Attributes in the relational schema becomes properties associated with nodes, and the join or foreign key is a relationship. So let's take a look. So here we have this, we directly create a bunch of nodes, and then we can use this match. So basically we can actually use match during the graph creation. Basically we have a match R1, R2, and then we have this where R1.b equal to R2.b, and then we can create edge R1 goes to R2. Similarly for this one. So without this where, we basically have a Cartesian product, meaning that we have a complete graph, meaning that for any pair of nodes, there's an edge. Where in this case, it's not necessary. For instance, the R2 doesn't have edge, goes to R1. So the resulting graph is kind of like it can be visualized as following in the Neo4j. So observation is that first, Neo4j doesn't really have notion of undirected edges during graph creation. User can ignore directions when they query the graph. And second is, unlike a relational model, part of the join computation is done during the graph model creation when you create relationships. So recall semantics of semi-join in the graph, meaning that A semi-join B means given a set of starting points vertices in B returns a set of vertices in A that connect to those starting vertices via edges. So so a multi-way join query is the same as a fixed length path query. So for instance, in Cypher query, we can naively just write something like this. Like we want to have something like R3, R2, R1, and then we have specified conditions R2.a equal to R3.a and R2.b equal to R1.b. So once you run this queries, actually you can when you try to understand how this one gets implemented, you can see here's the plan for the Cypher query. Okay, so here we can see a bunch of nodes, and here, for instance, we have this expand all. So expand all is you can symbol this as a physical operator inside Cypher, where it's given a start node, and depending on the pattern relationship, the expand all operator will traverse all the incoming or ongoing relationships. So here, relationship is the same as edges. So in a way, you can symbol this as a breadthwise expansion of a search tree. And then basically this expand all plus the next step filter this node is kind of like implement the logic join. So the execution started with R1 and follow the edges from R1 by one more level to find all R2 that satisfy the following condition. And then we can use filter to apply this predicate R2.b equal to R1.b. Yeah, so again, so just a reminder that each match where can be solved as a slide from where. So actually, so this one actually is a good case that this query actually is a good standard way when you want to write a join query. If you want to do you can, I mean, on the technically you can directly translate SQL queries into Cypher like following. For instance, you just want to match some nodes and some nodes satisfy some conditions. And once you have the plan, then basically you can see that actually is just say here we have a table scan, and here we have another table scan. Here we're doing this hash join, and then we have another table scan, and then we do hash join. So it's like left deep pipeline join of three relations, and then at the end we just produce result. But once you run that, you're probably going to see some similar warning message like this. It says this query builds a Cartesian product between disconnected patterns, meaning that technically we can write queries like this, but this is not a good way to write Cypher query. So in a way that the above Cypher query is anti-pattern. So the last components of today is really about to just showcase about to try to reinforce this point about the difference between relational graph. So this is actually a term project done by a student in the same class, not really the same class, but a graduate version of database offering in spring 2019. So the goal is to enable run queries against a large collections of data gathered from students' workplace. So for instance, the example query is where are all my photos? And similar queries could be query against files stored in the S3 bucket or query against log files collected over time from different services on AWS. So the method is that the method of study is that they model the data both in relational model and in the graph model and compare the performance. So the first one is that for instance, we have a query that we want to return full paths of files that match a given file name, and this is actually the relational query, and this is actually the corresponding Cypher query. So as you can see, the Cypher query is much shorter than the SQL counterpart. So that means that it's easier to to develop and maintain the like Cypher queries versus SQL query. And this table actually shows the performance, like meaning that for instance, we have the exact same query, find the exact all.txt files, and then we have database Neo4j, and they run exactly the same query and implement using SQL, and then run it, and then we compare the performance. As you can see, in some cases, actually, surprisingly, that relational model actually works pretty well compared to the corresponding Neo4j version. So in this case, we want to find all the TXT other limit by 1,000. In this case, SQL queries only takes 56 milliseconds, where corresponding Cypher query takes around 600 milliseconds. And the second point is that Cypher query still needs many hand tuning to reach extendable performance. So as you can see here, so basically we can implement the same query using kind of like different syntax of the Cypher, and actually it will gives you a very different performance. For instance, it can range from around 700 milliseconds to all the way to the 4,000 milliseconds. So the conclusion of today's lecture is that, just quickly recap, we introduced the edge label graph and also poverty graph, and we discussed their difference with each other and also with relational model. And we introduced the graph query languages. There are a bunch of them out there, like Sparkle for RDF, Gremlin, Cypher for poverty graph. But we introduced three important usage patterns in the graph query languages. One is graph pattern matching, and then path query, and then the navigational graph pattern matching is just a combination of the previous two. Then we demonstrate and practice those usage patterns in Cypher with Neo4j, and then we introduce this Cypher query profiling in Neo4j, basically using exactly explained commands. And then we take a look at a case study on the difference between relational model versus graph model, where graph query is easier to write and maintain, and Neo4j still probably has a long way to build sophisticated optimizer like Postgres. Okay, that's it. So that's the end of the today class. So probably you're gonna want. I think probably you're gonna do some lab or homework around Cypher and Neo4j, and let me know if you have any questions. And the slides already uploaded in the box. Feel free to take a look. Okay. So, yeah, I think that's it. Class ends, and see you next time. Sure. Thank you. Thank you for listening. Thank you for chiming.